Hey students, this video is about the aluminum lab calculations. And we're going to start with number 1 after your data table. I'm going to bring it up on my screen. There's our aluminum lab procedure. Here's our aluminum lab calculations we're going to be working on. And the calculations start on the next page. First question is, why is the inside of an aluminum can lined with a plastic coating? All right, so why is there, between the Coca-Cola and the aluminum, why is there a plastic coating? Coca-Cola has lots of different ingredients. It also has carbonation to it. And when carbon dioxide dissolves in water, it's going to form a little bit of carbonic acid. See if that helps you think about why there is going to be a plastic coating that we had to scrape off before we reacted our aluminum. That one we've actually talked about in class before this point. The next one is discuss the mass of your beaker and reacted filtrate before the aluminum was formed on day 2 and after the alum crystals formed on day 3. I'll show you where that is on your data table on the other side in a second. You are going to use numerical data, or quantitative data in your response and explain why the mass has increased, decreased, or stayed the same according to the law of conservation of mass. And you know the law of conservation of mass. Unit 1, we can't create or destroy matter. So if your mass increased or decreased, you got to tell me where that mass came or went. So let's find the alum crystals and before they formed and right after they formed masses on the data table on the other side. All right, here's your day 2 data, the mass of the 150 milliliter beaker and the reacted filtrate. And then here's going to be your mass for day 3, the mass of the 150 milliliter beaker and reacted filtrate with the precipitated alum crystals. And so that we can see this as a balanced chemical equation, I'm going to write it out for you right now. So here's our filtrate in solution. And actually, right before we reacted that filtrate, what we reacted it with was the sulfuric acid, the clear, colorless sulfuric acid in the fume hood in the front of the classroom. So you had your filtrate. That was what was in the 150 milliliter beaker that dripped through. All the impurities were left behind on the filter paper. We threw that away. This is the filtrate I'm talking about. You brought it up to the fume hood and we added the sulfuric acid, and then you stirred and you stirred and you stirred and you stirred and you stirred, and then someone else stirred for 5 minutes total. Right before you brought that to the front of the room, you wrote the mass down. That's the mass I'm talking about. So this mass represents the filtrate and the sulfuric acid from day 2. Day 3, what precipitated out overnight was your solid alum crystals. And you had this new solution as well that had other ions floating around that didn't solidify into an alum crystal. That's the mass from day 3. And your beaker just sat on the table overnight. Did it have a cover on it? According to the law of conservation of mass, the ions in the filtrate, the ions in the H2 and the SO4 sulfate, nothing was added into the system, nothing was taken away. Your alum solution or your alum solid was formed overnight, and they came from the ions in the filtrate and the sulfuric acid. There was a leftover solution. There's no gas here. Nothing could have bubbled away. There's no gas before and after. So nothing bubbled away. So what happened? Okay, well, think about that beaker again. You have your solid alum at the bottom. It's supposed to be my alum. And then you have all these other ions floating around in substance. What substance are those ions floating around in? I'm underlining right now is the AQ. Think about what that stands for. AQ stands for aqueous. Those ions in the filtrate, those ions in the new solution are floating around in water. What happens to water overnight? Can the mass decrease overnight by water evaporating if it's an uncovered system? That's what this question's getting at. And if your mass did not decrease overnight, you probably have the wrong masses from the procedure. You took your masses at the wrong time. So you're going to need to write me a note about reading the procedure properly. And if you read the procedure properly and have the correct mass, why day 3 is less massive than day 2 due to evaporation of water. Okay, number 3, we've got the chemical formula finally of our alum crystals. And alum, here's my formula for alum: potassium aluminum sulfate, dodecahydrate. And I would never ask you anything on this on a test or quiz, but you can definitely understand this. Potassium's a +1, aluminum's a +3, sulfate's a -2. There are 2 sulfates. So I've got a total charge of +4, a total charge of -4. So even though it wouldn't be on a test and quiz, still an ionic formula. And now I've got 1 formula unit, but I've also got this water component, 12 molecules of water. But 1 formula unit of alum, I'm just writing alum instead of the chemical ionic compound component there, includes 12 molecules of water. That is what this dot 12H2O means. Or another way that this was stated, why I had the procedure with day 3 up. As your solution of aluminum sulfate cooled overnight, that was your filtrate that was reacted with sulfuric acid. A new substance, potassium aluminum sulfate, dodecahydrate, that's your alum, those crystals precipitated overnight. What that means is that the 12H2O, there are 12 water molecules incorporated as part of the crystalline structure. Such compounds are called hydrated compounds, or they're soaked up with water. So what I'm going to show you guys next is not actually alum. What I've got here is sodium chloride. And sodium chloride is a simpler formula unit. Let's pretend that's a sodium, that's a chloride, sodium ion, sodium chloride, sodium chloride. And this crystal builds up because for every positive, there's a negative. Alum would be a little bit more triangular in shape. But the formula and my simplified structure here, sodium chloride, here's a sodium, here's a chloride, there's my formula. This is 1 unit of my ionic compound. That's why it's called a formula unit, not a molecule, because it's part of this bigger unit structure. And if it was alum and I had a formula unit in this open crystalline space, trapped inside this crystalline space would be some water, which is represented by my mole here. We're going to pretend that my mole is worth 12 molecules of water. So for 1 formula unit, there would be trapped inside that open space 12 moles of water. So you could imagine this whole entire structure saturated with moles of water. That's what this means. I'm going to go back to my shared screen. For every 12 water molecules, they're incorporated as part of that crystalline structure, or 1 formula unit of alum includes 12 molecules of water. All right, well, that's helpful. Now we got to do some work with the molar mass. All right, so I've got my periodic table handy here, and we're going to write down some molar masses directly from the periodic table and then add them all up. So potassium, I've got 1 potassium ion, 1 Potassium's molar mass off the periodic table is 39.1 grams per mole. I've got 1 aluminum in my formula. Aluminum's molar mass is 12 grams per mole. And sulfur comes up next. Let's be careful here. There are 2 sulfurs. Sulfur's molar mass off the periodic table, 32.1 grams per mole. Scooch over now. Let's deal with oxygen. We've got to be super careful with oxygen. Oxygen, there are 8 oxygens on the ionic compound side, but there are 12 times 1, 12 oxygens on the product or on the hydrated side of this ionic compound, which gives me 8 plus 12 is 20 oxygens. So I'm going to have to multiply that by the molar mass of 1 oxygen, which is 16. And then hydrogen, 12 times 2, I got 24 hydrogens I got to deal with. The molar mass of 1 gram per mole here. And when I add all of this up, after I multiply through, my molar mass ends up being 474.3 grams per mole. And I could write potassium aluminum sulfate dodecahydrate, or I could just write the word alum, which you'll see me do in problems 4 through 7. Next up, from your data, how many moles of aluminum did you start with? Show your work. So now what we're going to start doing is our grams to mole process. And what I'm looking for is a mole island to show you guys. We know the grams of aluminum. Now this is asking us to go to moles of aluminum. That's this next question. So we're going to go grams of aluminum to moles of aluminum. And if you look on your data table on day 1, you know the mass of your aluminum pieces. This is close to 1 gram. I'm going to use 1 gram in my calculations. You guys use exactly what you have written here, 1.02, 1.12 grams, whatever it is for you, you use your data, not mine. So I'm going to say, if I started with exactly 1 gram of aluminum, how many moles of aluminum would that be? And I know there are 27 grams in 1 mole of aluminum. I have that written up here. Cross multiply divide. When I did this, I ended up with 0.0370 moles of aluminum. And I want to make sure I have 3 sig figs because my balance gave me 3 sig figs. Better balance, more sig figs. But our balances only gave me 3. So leading zeros don't count, trailing zeros count when there's a decimal, which there is. So your number should be in the range of 0.0370 moles of aluminum. All right, next question. The overall balanced chemical equation for the synthesis or the making of alum crystals structure is as follows. For every 2 moles of alum, I needed 2 moles of potassium hydroxide. That was done in the video for you. You also needed 4 moles of sulfuric acid. That was done in the fume hood during class. The water, 22 moles, was incorporated in the solutions, as talked about in problem number 2 above. Then we made the aluminum into crystals of alum. Here's my alum formula. And I made 2 moles of alum for every 2 moles of aluminum. I also produced 3 moles of hydrogen gas. That was produced during the video with the reaction of the KOH. This is a pretty big balanced chemical equation, but it's done for you. And we just need to use this to go from moles of aluminum, which I have a number 4 up above, to moles of alum. And I'm going to write alum instead of the formula for alum. Once I have that, moles of alum, I can use the molar mass of alum to get to grams of alum. And again, you're using your data. I'm using, if you had exactly 1 gram of aluminum. So I'm going to pull this because now I know my moles of aluminum, 0.0370 moles of aluminum. And I want to go to moles of my new substance, with is alum. And for every 2 moles of aluminum, here's my mole to mole ratio, I produce 2 moles of alum. You need this step. And don't go changing this to 1 to 1. This is a 2 to 2 mole ratio. Pull the coefficients down exactly as is. I want to see the work. So even though you don't need to stick this in your calculator, I need to see it written down. This is proof of moles of aluminum transferring through a chemical reaction into moles of alum. But now I got my moles of alum, which is the same number, coincidentally, as moles of aluminum, but now it's a different substance. Now I can get to grams of alum. And I know in 1 mole of alum, because I wrote it up above, there are 474.3 grams of alum in every 1 mole of alum. So when I cross multiply, round to 3 sig figs, in a theoretical perfect world, there are 17.5 grams of alum produced. Or this is my theoretical yield if this lab was done perfectly, but we only have perfect on paper. What you actually produced, or your actual yield, you need to look at your data table on day 4. What you actually produced is right here. That's your actual yield. You actually produce that amount in lab with your group members. So we just need to pull that number once you subtract the beaker properly over here. That's your actual yield. Your actual yield is probably below your percent yield. So percent yield, if we remember back to the hoagie activity, that 95% hoagie yield, because 5 sandwiches were dropped or eaten, percent yield, the way you found that was you took your actual yield over your theoretical yield times 100. So your theoretical yield is from your perfect on paper theoretical work. Your actual yield is from your data table in lab, what you actually produced. And this number is probably under 100%. My question is, why? Why is your actual yield so low? Where did your alum go? We wanted the ions here in solution to precipitate out properly to form a solid. But where did those ions go? You got to think about your procedure. Those ions got lost somewhere. Maybe those ions got stuck on the filter paper. Supposed to be covered with impurities, but could there be material we wanted in lab? Let's take a look at the rest of our, let's see. Ooh, you had a beaker. Could ions be left along on a beaker? What other equipment did you use? Filter paper, beakers, ooh, decanted. Could anything gone in the sink? You were supposed to be washing with ethanol. Did your ethanol clean properly? Oh, you had a stir rod. Could any ions be left on the stir rod that were supposed to be turned into solid alum crystals? To explain your percent yield, what you need to do is identify 2 lab errors, not human errors. Don't tell me I spilled the beaker. Something you couldn't avoid. Give me 2 lab errors and explain how they affected the data you wrote down. How did it affect your data? Then, once you tell me if your data is recorded too high or too low, how did that affect your calculations? How did your data affect your percent yield? Is it too high or too low? And for the majority of you, the percent yield's too low. Where did you lose ions? Think about the equipment. That's your challenge. Bring that back to class and we'll talk more about it in the future. Great job, guys.